The third way of looking at probability, we've had probability trees, two-way tables, now Venn diagrams. So with the start of this comes a few definitions, and these flow right through the different ways of looking at it, but the Venn diagrams are the best way to view them perhaps first. First term is union. This formula here, in all its glory, is supplied in the formula sheet. And the key is that when we see U, it stands for union. Union means and or, so both happening at once. Union is when something comes together. The problem with union in a Venn diagram is if there is an intersection, if we just say, oh, the probability of A and B, we could end up counting the intersection twice. So that's an important thing, and we'll come back to that in an example shortly. Intersection, this is notation we've hit already. Venn diagram, it's nice and visual. The intersection is when A and B are both happening, so it's overlap when you look at it. Intersection is the term, and the N symbol is the notation. And if two things are independent, we've seen this already, we can find the intersection by multiplying the two probabilities. As long as they're independent, we can do that. The idea of mutually exclusive, some people tangle up with independence, but it's quite different. Mutually exclusive is when there is simply no overlap. The main time you may have hit this is if you've had a clash in your timetables. That's an example of mutually exclusive. If PE and for Z happen to be on in the same column at level 3, you simply can't take them both. So the probability a student takes one, the probability that a student selected takes both is going to be 0, no intercept. So we keep an eye out for that as a definition, it pops up. So a couple of examples just with a pack of cards before we look at it, just to get union and intersection. So A is drawing a diamond from a pack. That's 32 out of 52, 13 out of 52. Drawing an B is drawing an ace, so there's 4 out of 52. Those could both be simplified. If we're looking at union, the probability of drawing a diamond or an ace, that would be A union B. And the problem there would be there'd be an overlap because there's an ace of diamonds that would get counted in both. So we would, rather than just probability of an ace, probability of diamond and an ace, we have to go allow for any double ups, the intersection. So you've got all of the diamonds, all of the aces, minus the ace of diamonds because it's been counted twice. And that leaves us with a total of 16 out of 52, which we would simplify most likely. So those definitions sort of stick with us. So don't just apply for Venn diagrams, but they do apply elsewhere. But Venn diagrams are good visual. Here's an example, sticking with the subject theme. 30 students selected from, let's say, from year 13 this year. Out of those 13, 18 are doing bio, 20 are doing stats, and 3 have rudely chosen to do neither. Actually, there's quite a few rude students there. So show this on a Venn diagram. So always work from the middle out. So we have a problem here. We've got 18 plus 20, that equals 38. But when there's 3 that are neither, so the neither are over here out of either circle, and so there's only 27 therefore, but if you add 18 to 20 you get 38, so we have 11 too many. So of these students in these 2 rows here, some of those students must do both because that 18 and 20 don't equal 27. So there's 11 extra. So what we do is we decide on the 11 and we chuck the 11 in the middle. We say, all right, well, there's 11 that are doing both stats and bio. If that's the case, the number doing bio needs to be adjusted because its total is 20, but 11 are doing stats as well. No, its total is 18, apologies. So we just have to put a 7 there, and that gets you 18 bio students. We do the same with the stats, we say, wow, there's a total of 20, but 11 of them are accounted there for there. They're doing bio, so only 9, and those are doing statistics and not bio. And here for the union, and we've used N for number instead of P for probability, so the number of people taking stats and or bio is the number of people taking stats plus the number of people taking bio minus the number of people taking both, which gives us 27. Now, Venn diagrams, the probabilities, if I can just scroll it so we can see everything, we can go through these quickly. Probability that someone does both intersection, that's 11, the blue in the middle. Probability show that taking bio and stats are not mutually exclusive. Well, if they were mutually exclusive, the answer to the previous question would have been 0. Because is it possible to take bio and stats? Yep, in fact it's quite common according to these figures. So they are not mutually exclusive because you can take both. What's the probability a student does either bio or stats or both? Well, that's the 27 out of 30. The probability that a student does bio and not stats. And now just have a quick look at the notation on that one. So that's the probability that they don't do stats, so that's a complement, and they do bio. So that would be these people here. They do bio, but they have shunned statistics, which is very hard to understand, really. And then the final one, bit of a conditional job. What's the probability that they do bio given that they do stats? Now the good thing about given, or conditional, given that they do stats, then it's just this circle, please excuse my graphics. There's 20 students in total, so the 20 goes immediately to the bottom line. Out of those 20, how many do bio? The 11 in the middle. Okay, so that's 2 by 2 Venn diagrams, and we'll look at the 3-way ones in the next clip.